Really glad to be here in Ann Arbor. I had one previous visit to Ann Arbor, but you're right. This is my first time at the University of Michigan. It was to visit a company called AISI, which I don't know if it exists anymore. It was a computer vision company, actually. So glad to be here. I'm going to tell you my life story, as Jeff said. I was born in LA. You see the little plane? That's Los Angeles. My family moved to New York. We didn't like it. So we resettled in Virginia, where I went to Acton High School, and also Virginia Tech undergraduate. It's a lot like if you've been to Purdue, and I was at Purdue yesterday and this morning, it's a lot like Purdue, but with mountains. Same sort of vibe. And at that point, I got in my very obnoxious Camaro and went to Texas, where, as Jeff said, I worked with Al Bovick. I should say Emmy award-winning Al Bovick. That's right. And Motorola, Jeff's right again, sponsored my PhD. I spent a year out there working in a fab, which now has come back into fashion, fabs and manufacturing. First job at OSU, Oklahoma State, Cowboys. Got in a pickup truck and I went back to my home state around 2000. And I've been working at the University of Virginia for 2 decades. This is my family. On the left is my nuclear family, at least. On the left is my son, Colby, who was a third-year ECE student, majoring in electrical engineering at Purdue. Saw him last night. My wife, Sabrina, and my son, Henry, who's a first-year student at, that's what we say, at UVA in biology. I also spent 3 years at the National Science Foundation before taking this chair job. My replacement is none other than the illustrious Alfred Hero. So I don't know if I can claim that he's my replacement because he's has big shoes. All right. So this is my lab. It's called Viva. And Shivri Mukherjee was a member of my lab. He now works at KLA Tencor in the semiconductor product sector. These folks over here are my most recent graduates, my 6 most recent graduates. I've been working for 35 years, but this guy, his first day at Meta. His first day at Meta, he's already making more money than I'm making. So. Don't follow an academic career if you want to make money. These 2 people contributed to the talk. Shomi Guha, who's part of my West Bengali pipeline, and Matthew Corbin, who's a postdoc who did the transformer work that you're going to see. I'm a department chair, so I reserve the right to brag on my department for a minute. We had 5 assistant professors on my faculty in 1 year win the NSF Career Award, which was extraordinary until 2 others came later in that cycle. So we were ripping off the University of Michigan and calling them the Fab 5, but now I guess they're the Fab 7. If you don't know the history of the University of Michigan, maybe some of you graduate students are more disengaged from the history of the University of Michigan. 5 freshmen started for the basketball team, which was extraordinary in that time. They wore baggy pants, and they almost won the national championship if it wasn't for a boneheaded move, which we won't go into. So we can talk later about that. But these are some of my young folks that are really killing it over at UVA, and we'd love to have, we've had Jeff before, for sure. We'd love to have you over to visit. It's a beautiful campus. This talk, 20 minutes or so are unapologetically pedagogical and might be telling you stuff that you already know. That's okay. I mean, it's like going to church. You don't learn anything new at church, but you get reaffirmed, right? So you can be reaffirmed if you're already an AI master. I'm going to talk about transformer, but I'm going to talk about diffusion network first at a very basic level. I taught my sister this lecture, and she's a biologist, so she got it. Then I'm going to talk about two advances that we made in our lab in both transformer and diffusion network, not in that order, that hopefully will be new to everyone in the room. And then I'm going to pontificate at the end. So I'm not exactly fresh onto the AI bandwagon. My dissertation was published in Transactions on Neural Networks. My advisor, which you've already seen a picture of him, a good-looking guy, called me in the office when I was about to graduate. He said, "Son, whatever you do, don't admit to anyone on an interview that you do neural networks." And boy, has it changed in 20 years, right? Now it's a hot thing. But this really, the students, you should realize, this is an unprecedented time. I liken it to when I started graduate school and they said, "Hey, Scott, there's this thing, it's called the internet, and you can get your own email address, and it's going to change everything." This is an unprecedented time with the advent of AI. 8 or 9 years ago, the top AI article in the New York Times was on one-shot learning. And one-shot learning just means you see the alphabet once and you can recognize it the next time, right? Maybe computer scientists are into that, maybe electrical engineers are into that, but it's boring. Fast forward to last year, for the first time in history, normal people are using AI in their lives. School, home, work, cheating, doing whatever they want to do, right? So it's a crazy time. My time at NSF, SIZE is basically the computing portion of NSF, which they separate from engineering for some reason. My time at NSF, when I got there, about a fifth of the proposals were on ML, machine learning. When I left, just 3 years later, exactly 3 years to the day later, and Al Hero entered the Zoom doors at least, 80% of the proposals by title were on machine learning in my area. So it's sort of crazy. One of the morals of the story of this talk is that you might do research on breaking rocks, and you might be a great rock breaker. Keep doing that, but you ignore AI at your own peril. So you've got to at least be cognizant of what's going on in machine learning and AI to have some success in the funding world, my opinion. When I was in grade school, elementary school, they told me the top journals in the world were Nature, Science, New England Journal. Hasn't changed much in 50 years, right? 2023, last year, look at what's happening. IEEE CVPR, are you kidding me? What is that? That's a conference. NeurIPS, ICLR, and there's several lurking down below there. Engineers, computer scientists, are now having the same impact that the great scientists in science and nature have had and enjoyed for the past half century. So it's a crazy time. I was watching 60 Minutes the other night on Sunday, and Sundar Pichai was on, and he said, probably a comment that he regrets now, we view AI as a black box. The real moral of my talk today is AI is not a black box. And so it has many forms, but it's something that we can engineer and know. So let's start with autoencoder. Autoencoder, I'm showing the encoder a 3, handwritten 3 from the MNIST database. And basically, I'm representing the 3, which is like 784 pixels, with maybe 30 variables that we'll call latent variables. It's a abstract, a reduced dimensionality representation. Decoding takes those 30 latent variables, maybe, and recreates the 3. We don't need to label these data. This could be unsupervised. We can just check reconstruction error to see how we do. People at Michigan have been coding and decoding for, half a century, right? So this is nothing new. One twist on this is if we make those latent variables random variables and we force a distribution on those random variables. Maybe they have a certain mean, maybe they have a certain variance. That's an autoencoder. That's a variational autoencoder. Okay? So, what's a diffusion network? And you've heard all this about diffusion. Maybe you know everything. Well, a diffusion network is just a concatenation of many variational autoencoders. Maybe 500, maybe 1,000. So we have like a forward process. Think of it as encoding. But in this case, we're encoding to the same dimension as the input, which is not really the spirit of encoding, but follow with me. We add some noise. We add some noise. We add some noise. We add some noise. Maybe we do it 500 times. We can all do that with MATLAB. I don't know if you can do it with Python. It depends on your skill. But that's the forward process. And then we get to a point that's all noise, right? It's indistinguishable from just white noise that we generated with MATLAB. Then the reverse process goes like this. Take away some noise, take away some noise, take away some noise. And we get back to this face of a person that doesn't even exist. How do we do these steps? Some simple neural network like UNet, which I'm not going to cover today. But it's a very simple step, removing some noise. And we've been removing noise in image processing, Jeff, and there's a lot of respect for the MR community here, including Jeff, including Doug and others. Good history. But they've been removing noise for decades, and that's all this does, right? Now, we can become like a deity and play with these random variables here, and then maybe generate a new face. And it's freaky. You should play with it if you haven't done it. It will mess with your mind. So that's a cascade of variational autoencoders to do a diffusion network. The question we asked in my lab that my PhD students show me, she's very good, asked, hey, as Jeff said, we care about biomedical image processing. We love ultrasound, even though ultrasound images are ugly, but that's what we love about them. We love speckle. Can we despeckle an ultrasound image? And here, with the diffusion network, and here, the noise is not additive, it's signal dependent, it's multiplicative. The answer turns out to be yes. And we've submitted a TIP paper on this, so if you're one of the reviewers, accept without changes, maybe. I've only had that happen once. Have you ever had that happen? So yeah, accept without changes, please. So here our model is not just adding noise, it's adding noise times signal, you see? So we immediately go to the homomorphic domain, where logarithms make products into sums, of course. But then our question was, can we use the machinery that's existing from the additive model? And it turns out the answer is yes. Show me proof that the forward process is indeed Gaussian, which you could say is engineered or by design. It's not that extraordinary. But even more extraordinary, she showed the reverse process is Gaussian with known variance, but unknown mean, because we don't know this guy. That's the beautiful image. So what do we do? And once again, what is the forward and reverse process? Forward process is adding noise, and in this case, adding multiplicative noise, and the reverse process is taking it a little bit away at a time, right? So what we're going to do is, in our latent space, remember our variational autoencoder, we're going to enforce a distribution. We're going to enforce the forward and reverse process to have a similar distribution. And how can we do that? Well, they told us in school there's something called KL divergence, and so Kullback-Leibler distance. And so we can use that in our loss function. And we can also have another term that minimizes the reconstruction error, an L2 norm. So pretty simple loss function. And what we can do is then we can basically take away a little noise in the multiplicative sense. And the cool thing that Shomi proved in her paper, who knows how long it will take? 6 months to get a review? I don't know. What she proved in the paper is that this multiplicative model can be implemented in one step, one denoising step. Oh, and by the way, this is on on archive. So if you search for Guha and Acton on archive, you'll find it. Let me show you some examples of this diffusion network. It's pretty cool. So like here's a noisy portion. This is like, I can't remember, this is like a cyst. And here's our denoise version. Here's another noisy one and a denoise version. So those are pictures. Ed Delp, who taught Jeff a class and has been a good friend of mine at Purdue for like a long time, told me you should also show where your method breaks, and I'll do that later.
Those are one-step denoise?
One step, can you believe it? And so 22 years ago, we made this paper, SRAD, Speckle Reducing Anisotropic Diffusion. And the goal is basically, here is to maximize the peak signal to noise ratio or the structural similarity measure that my advisor keeps getting thousands and thousands of citations for every year. And as noise gets worse, this alpha is basically controlling how much noise we're putting in the speckle. Oh, and by the way, physicians and ultrasound people are very resentful if you say speckle is noise, because noise is signal. I mean, speckle is signal. So we're doing really well when the noise gets bad compared to my original paper and several others. These are all deep learning methods, so to speak, and these are all conventional signal processing. Back when people understood physics and mathematics and principles behind engineering. So check this one out. It's just now in archive. That's our diffusion work. It's ongoing. I want to tell you a little bit about transformer, and I'm going to introduce it by giving a 7-minute version of my explanation of ChatGPT, of the core of ChatGPT. You may know everything about it, but let me try to explain it to you in 5 minutes. 5 to 7, you can time me. It's really, at its core, just a fancy autocomplete machine. I know there's a lot of bells and whistles. I gave a 3-hour talk on this subject to my lab with the purpose of trying to understand it myself. And I based a lot of my talk on Steve Wolfram. This guy's been doing incredible stuff since like 85. So basically you give chat a string like, the best thing about AI is its ability to, and it gives you it gives you a set of words and their associated probabilities in bunny quotes. If chat is feeling really hot, it might do something crazy like select do, or really cold, it might be more conservative and say learn. So basically, you can play with the interface. And this is what Steve Wolfram does. He shows you how to play with the interface, the SDK, for ChatGPT 3. And that's what I'm going to talk about because I don't know anything about 4. It's more secretive. So if you do this like 7 times, query the same interface 7 times, you get a rambling sentence like this, autocomplete, right? And ChatGPT may not be smarter than any Michigan student, but it's read more than any Michigan student. It's read like 5 to 10 billion words, right? So it's read a lot, and it knows. I mean, this is another unsupervised problem that's awesome, right? You try to predict, you give it this, and you try to predict what comes next. You already have examples of those sentences to train on. So it's an autocomplete. So engineering, and I'm looking for the purposes of this talk, I'm going to consider computer science also engineering. Engineering, we talk about input and output. What's the input and output of ChatGPT? It's words. And those words are converted into tokens. Those tokens are integers. So the is something like 780 something, I can't remember. And there might be partial words like ized or pre that are also tokens. But we use about 50,000 English words day to day. And there's about 50,000 English tokens in chat. French use more or less. Less. They're more conservative with language. And we'll do some French. So inputs are tokens that are integers converted into an embedding. Think about 12,000 numbers that are 10 bits in length for each word. The embeddings are coded in a way to encode the position within the sentence. I'm going to show you how chat does that real quickly. And then transformer network, which we're talking about just real briefly, can consume all of these vectors simultaneously. It's beautiful. And the transformer network was just written by a young person in the Bay Area, like some of you. So maybe you could come up with the next thing. Who knows? Embedding. Instead of ChatGPT, it's 12,000 numbers, 12,288. Basically, I can't show 12,000 dimensions very easily, but I can show two. So here's a snapshot of 2 dimensions. And you see that words that are like each other, alligator and crocodile, are close. This also allows, to have words in context. It allows you to do math with words. Like, for example, king minus man plus woman equals queen. And that's a classic example. There's more controversial examples that show bias, but we won't get into that. And bias is definitely there. Bias is in the data. So people have been doing embeddings for 20 years, at least in language models. I don't work in that area, but it allows you to do math with the words. So all the tokens are converted into embeddings. And then, if you're a math person like Jeff, maybe you'll appreciate this slide, or if you're a visual person like me, you'll appreciate the next slide. Basically, we're adding these sinusoids that depend on what? Depend on the position within the embedding and the position in the sequence. And so we're changing these sinusoids based on the position of the word in the sentence. I am a robot. I is first. Am is second. All right? Now, that's the mathematics. What you're really doing is adding this picture, to your embedding vector. And that sounds crazy, but it's been shown that you can then afterwards find the relative positioning between words even after they're decoupled from their position. Okay? So every embedding vector gets a position added to it. And it looks like that mathematically and that visually. Of course, this would be 12,000 long, and ChatGPT 3 is only 512 in this example. And 100 words, that's reasonable. 100-word sentence. So then we compute attention. And what is attention? Well, attention, we might have called it attention correlation back when I was in school. But, it sounds cooler to call it intention. And in computer science, they use words like query, key, and value. Query is saying, okay, here's a word, maybe a Tudiant student. Who gives me attention? Well, it turns out I gives a Tudiant a lot of attention because it tells you what I am. A Tudiant tells you what I am. I am a student. The keys are the states of the other words, including the word that you're looking at yourself. That's hence the word self-attention. And the values are actually the actual embedding vectors. So we're going to weight these values by basically something that depends on the product of query and key. It's that simple. And there's some other bells and whistles. We're going to normalize attention, and we're going to make it look like a distribution by softmax operation. But really, it's query times key. And that's going to weight the values that we use to represent the words that are in our sentence. So I'm going to use this translation example real quickly to show you what attention means. All right, so self-attention, what's the purpose? The purpose is context, because look at the first sentence. Server, can I have the check? Server has a transactional context because it's check attends to it. In the second one, server has a computational context because crashed attends to server. All right? So that's the idea, is adding context. How do we compute it? Well, it's really simple. Query and key are multiplied. And there's linear weighting, which means there's no nonlinear element to these weights. And as I said, we scale and then do softmax. And so those are raw attention values. And these are attention values after we normalize. And then why do we normalize? Well, we don't want gradients to be too big, too small. Those are problematic. Is this very heuristic? Yes. But this is what's going on in the transformer. And so then we're going to weight these values by this attention matrix. And when you play the Game of Thrones, you live or die. I'm just telling you that. So you can see some interesting ones in here are like between play and game. That's not very good. Let's see, game. Yeah, game and game is high, but Game of Thrones is, so moderately high. That's attention. And it's, scaled and softmaxed. Softmax just means everything lives between 0 and 1, adds to 1. So, the transformer. It's a lot like what I was talking about with, the autoencoder, in a sense. We're taking words, je suis étudiant. I'm a very poor French speaker. My son's a lot better. I don't know if did you get good when you were in Paris? So, je suis étudiant, we convert those into embeddings, tokens and then embeddings. We add the position. That's what goes into the encoder side. And maybe there's 20 levels here, but I'm just showing you one. We get latent space variables, just like we did before. We feed those into the decoder, and the only difference between the encoder and the decoder is that there's these links called encoder-decoder attention. And I'm showing that over here in this beautiful example that somebody else made. This guy, I don't know how to say it. And one thing you'll see is I am a student is our output, which is a good output. A, which has no parallel, doesn't give attention to much else in the sentence because there's no parallel in the French counterpart from the encoder side. So this is really, and you can put together a simple transformer like this, maybe with an hour of programming. It's really fun. So what are we doing in the lab with transformers? You didn't come here just to hear about chat. Well, we like video. And we have funding from the National Science Foundation to observe classrooms and to evaluate what happens in the classroom. Is that crazy or what? There's actually rubrics that teachers use for new teachers. And there's activities within these rubrics like teacher guides small group to work together, teacher lectures, teacher demonstrates. And so we want to know, can we find these activities with a transformer? And what are people doing in the art? People are using something called Vision Transformer, which takes the ChatGPT-esque model and instead of using words, uses patches of images. And instead of using position in a sentence, they use left to right, top to bottom position in the image of those patches. We said, hey, wait a minute. Videos have moving things in them. And the semantically meaningful things in videos are not patches, but they're people for us, and students, and teachers, and books, and computers, the objects they manipulate. So in our transformer, we first do object detection and people detection. And so the only queries, remember query key value, the only queries are people. The keys, the other states, are people and objects. And because we believe that videos are interesting because things move, we're tracking motion. In motion, we're going back to 1970, and we're using optical flow. And then we're making this a multimodal problem. We're going to call motion a different mode than geometry. And so now we're going to compute attention between geometry and motion, motion and geometry, motion and motion, geometry and geometry. And that's what you see down here happening. And we also say, hey, this left to right, top to bottom encoding of position is bogus. We're going to use 2D position. And temporally, we're going to do something really interesting too, I think, which is to say we're going to not give attention just between consecutive frames. We're going to try to find keyframes that stand out in distribution from the distribution of the features in the sequence, and then compute temporal attention that way. Because videos aren't just snapshots, they're a sequence in time as well. So they're somewhat three-dimensional. And by the way, this is actually on the PAMI website now. And Al Bovic, when he heard that I published in PAMI, he gave me a hard time. Oh. So you feel free to give me a hard time. He said, don't publish in the yellow journal. Anyway, so we thank NSF for support on this little project. So the position, so we're basically tracking, we're doing like a really low budget tracking over just a small sequence of frames by optical flow. And by doing that, we don't confuse this player with this player by just keeping the same 2D position. We know that this player is moving this way, or I guess he's moving that way, he's backing up, and that player is moving that way. So our positional encoding have these deltas, which are the change in positions that we observe from optical flow. Really simple. So, and also it's a two-dimensional position. There's an X and Y component instead of just a one-dimensional component. And we had to figure out how to encode that. What else is going on here? Attention is really the same thing. Remember I told you attention is just query times key. There it is. And this is a normalizing term. Attention is the same thing, but we have geometry to motion, motion to geometry, geometry to geometry, and motion to motion. And my postdoc has examples where he thinks all of those are independently relevant. So the last thing we're doing is we're saying, okay, if attention is correlation, think about it. You're going to get a lot of attention in videos temporally between consecutive frames. We contend that that's meaningless. So what we want to do is find the keyframes first, and then we compute attention between those keyframes. And what are the keyframes? And I'm going to botch my Bengali here, and I'll say Mahalanabish. The keyframes are the ones that have greatest Mahalanabish distance. What do you think, Shivadi?
That's pretty good.
Yeah, thank you. From the distribution of features in the sequence. So we compute this distance, and we use the distance inspired by this distance. It's not exactly the same thing, to figure out our attention. And let me just show you an example. Here's an example with a triple jump. It's not in a classroom. If you look at standard attention, if you were just doing like correlative attention, you'd say, okay, these two frames have a lot of attention. But what does that tell you? What's cooler is that basically in our version of attention, there's a lot of attention between these two frames, the jump and the landing components of the triple jump. I'm a notoriously poor jumper, but that probably goes without saying. So anyway, this is just our angle on finding keyframes. Maybe there's a million ways to do this, and then computing attention in time between these keyframes instead of having some meaningless measure of consecutive frame attention. And that's in this paper. If you want to look it up, this one right here, if you look up on the PAMI website, which has a really ridiculous impact factor of like 26 now.
Scott, can you just clarify, what is the high-level thing you're trying to solve with these methods in the video?
Oh yeah, great question. So what we're trying to do is we're trying to, and there's 24 actions that we're trying to detect. And so at the end of this transformer is a classifier, and that's the output. It says, it goes on for one of these actions, like working in group is one of the actions. Students sitting is one action. Teacher standing is one action. That sort of thing. And then we have like a what do they call it? A dashboard that displays it to the teacher, and she or he gets certain statistics about what happened in the class. So yeah, it's that great point, Jeff. I get buried in the weeds. So action detection is our output, and specifically in the classroom. And what's cool about this classroom work is like everyone loves it. Republicans, Democrats, you know, it doesn't matter. Everyone likes their kids to be taught, right? So it's good. And the nasty thing about computer science and computer engineering, and I guess electrical engineering at this point, is that to publish you have to compare to like 20 things now, right? And if they're 2020, it's like way too old. So the reviewers reject you. So these are data sets that are publicly available, and smashed is what Matthew calls this method, his transformer method, and it's doing pretty well. And basically, this is called mean average precision at 50% overlap. You have to at least have your bounding box 50% overlapping, and these are the types of things that he had to do to get published in PAMI. And you can see this data set, Ava, is pretty challenging, as is Epic Kitchens. That's a fun one. Cooking. Now, here's my nod to Ed Delp and showing where it breaks. We tested our method. These aren't classroom videos, but we tested our method on old movies. And there's an old movie database. It's really fun to play with. And in green are some of the true positives, but you see in red some of the false positives and false negatives that we get. Oh, and by the way, we have 500 hours of classroom video, which down to the second have been annotated by 3 human observers. So we have quite a nice database, and we're going to do a Kaggle competition. You could win $100,000 if you compete, and I'm serious. You'll enroll in our IRB, our human protection, and you can compete with the data to get the highest classification of activities, and we have $100,000 in prize money, and I think we're going to give like 50, 30, 20 or something like that. So win 50,000. But here we thought we saw bending or bowing, the transformer did, and it was a false positive, for example. Here we didn't catch carrying or holding, and there was carrying or holding, according to the human observer. Just some examples. So now I'm into my pontificating, my preaching. So that was our transformer work. Catch it on that PAMI article if you want to know more or talk to me. There's a ton of problems that Michigan students. By the way, Michigan has a great reputation in ML AI, and so I know there's some exciting things coming out of Ann Arbor. Here are some areas that I think we could make a contribution in, and one is simulation. Simulation sounds boring. It sounds like playing computer games. But machine learning is hungry, right? It's hungry. And when we were working on stupid problems like Netflix, like you give me the last 20 movies that you watched and I predict the 21st. We had abundant data. We had clean data. Now you get into the scientific realm. The scientific realm, my colleague Andreas Gallman, it takes him one day to make one image of bacteria on his microscope. So he has 100 or so images, but it's not good for training to do segmentation or tracking of those bacteria. So the key is good simulation data, realistic simulation data, and maybe the state of the art a couple years ago was GAN, Generative Adversarial Network, and maybe now it's diffusion network, but who knows what it will be next year. You'll have to invent it. I would like to contend, and by the way, yesterday I gave sort of a version of this talk to Purdue. Charlie Bowman lost a gasket on this slide because I contended that attention is really correlation, right? So we know neural networks of today know a lot about what correlates with what, but we don't know what caused what. For example, is a symptom a result of a disease, or is it the thing that caused the disease? So we know nothing about causality. And Charlie's point yesterday, which I thought was that I took well, was basically we haven't even defined causality properly in the context of machine learning. So maybe that's a problem that you all could work on. In other words, he thinks it's ill-defined. There were some graph people in the audience that thought maybe directed graphs could be the solution. I think this is a problem to work on, causal machine learning. Of course, everyone knows that we should be working on explainability, right? And the moral of my talk is AI is not a black box. But if we're ever going to have AI or machine learning, and maybe we don't want it to be adopted, but if we want it to be adopted in a certain context, like medicine or in the classroom, we're going to need to be able to explain why it breaks and why it succeeds. And I'm working with Dr. Musa and Dr. Shabani on basically planning software for doing a procedure in the brain. It's an ablation, a burning of the brain for people that have essential tremor. And it works fantastically, but we need to know why it doesn't work when it doesn't work and why it works when it does work. And so my student, Samarth Singh, is basically trying to develop explainable methods of showing the false cases and the successful cases in the surgical planning. Surgery is probably the wrong word. It's more of a non-invasive treatment by focused ultrasound. So by the way, look at YouTube on, I guess, UVA focused ultrasound. Amazing procedure. People go in not being able to write their own names or brush their teeth. They come out perfectly functional in general. Continuing with my preaching. I really believe in cross-disciplinary research. Professor Fessler does as well. We just chatted about it before the talk. But I believe it has to be bidirectional. If you're the computer science or the computer engineering person, you're not just a person that's cranking out data. And if you're the biology person or the medical person, you're not just a data source. A good relationship has to be mutually beneficial. And it's hard to get, and it takes time. And this is what I'm totally all about at UVA. I'm working with chemists, working with biologists, medical doctors, learning so much. You've got to learn their vocabulary. You got to put in the work. They have to learn a little of your vocabulary as well. So I'm going to end with some mathematics, 2 lemmas and a proof and a theorem. All right. So my lemma is that you really can't ignore artificial intelligence. Even if you break rocks, you can't ignore artificial intelligence. My friend Fred also contributed a lemma, which is that a proposal would be more successful with current technology than it would be with 8-year-old technology. Because this field is rapidly evolving, right? He also has a corollary, which is you're not going to get funded in 2024 by sending NIH your suggestion to do UNET on medical images. You know, it's been done, right? So I'm just encouraging you to keep current, either with your collaborators or if you're the creator, yourself. So you have to keep current. You have to have some curiosity. That's the first slide. Putting those 2 lemmas together, some might say lemmata. The theorem, which I'll leave to the students as an exercise to prove, is that we will be more successful in this room if competent users team with competent creators. And I know they're not necessarily completely separate in the Venn diagram, but I'm encouraging folks in medicine particularly to team with competent signal processing people. That's my field, signal processing, that also understand machine learning. And as I said, the key moral of the story is it is not a black box. We can understand these systems, and we shouldn't teach black box mentality. We shouldn't tell our students to just download some network and apply it on data. We should teach our students to look at the papers, look at the mathematics, to get under the hood, and to pop the hood on artificial intelligence. So thanks a lot for hanging in there for this time.